The protocol itself is as simple as possible. You have a single byte for the application. You have a single byte for the verb. The application might be for the monitor, if you want to read and write the memory of the debugger itself. Like if you want to check its version number, you actually just grab a value out of flash memory. If you want to know which chip is in your version of the debugger, you can just grab its model number out. There's a different application for every target. So you set this byte to a different value if you want to target an MSP430 or an AVR, and all of this code resides in parallel. There's no advantage to keeping it separate because there's enough flash memory to hold all of it, and the code is being executed directly from flash memory. This is not like a PC where you have to copy things to RAM first and then execute them there. And being written in C, you don't have the overheads of proper class inheritance and all of that stuff. The code also becomes a bit of a spaghetti mess, but that's manageable. And then after the verb, you've got a 16-bit length and then some data of up to that length. As a matter of courtesy, the Python client will check to make sure that there's enough buffer space for whatever it's about to write in. The firmware is written mostly in C with a little bit of assembly, and been over this. The only things to stress, though, are that this whole thing runs in less than 400 bytes of RAM. Everything else can stay in flash, and everything in flash we don't have to worry about. The limit for the mass production cost of this device is that if it ever goes above 512 bytes of RAM usage, the price of the chip almost doubles. So that's a hard limit that I'm trying to stay under, such that I can continue to manufacture these with the cheap chips. I've got versions at 3 megahertz and 16. This is a lot less powerful than the PCs that you're used to. Also of note is that every instruction takes a fixed amount of time to execute. Some instructions take more than others, but you don't have to worry about multitasking or threads colliding or anything like that. The client, written in Python, does the mid-level and high-level. So the first chip we'll talk about is the Chipcon 2430. This is an 8051 microcontroller, which was one of the very early single-chip computers out of Intel. It works with a single byte opcode, optionally followed by parameters. You can actually write this machine language or read it by using lookup tables on paper. And it's used for very small IPv6 implementations. This is the device here. You can actually give it an IP address and ping it. This is it on a keyboard. That little chip in the middle is the entire computer. RAM, ROM, flash, EEPROM, everything. It's documented in a 16-page document from its manufacturer. It uses an SPI-like protocol, meaning that you've got a clock. Each party writes on the rising edge and reads on the falling edge. But the data line here is bidirectional. So the very last word can switch directions, allowing data to come back from the chip to the host. This is what it looks like on my high-tech chalkboard. I don't have a chalkboard anymore, I miss it. To start the debugging sequence, all you do is pull the reset line low, which sort of suspends the chip as you're about to reboot it. And then before you raise it high, you send 2 pulses on the clock. Once you're in, the sequence is that you send a single command byte along with 0 to 3 data bytes and 0 or 1 return bytes. And this is all encoded in the command byte. So if you look at the 5 most significant bits, that's the instruction. There's a single bit that describes whether or not there's a reply, and there are 2 bits that describe how many parameters you're throwing after. If they're 1, 1, you send 3 bytes. This is how the data looks on the wire. You send the most significant bit first. Each party will write a value on the rising edge, so you'll see that the rising lines are parallel, and then it's sampled on the falling edge, and you'll see that there's never a transition on the lower signal, the data signal, as the clock line is falling. And that's how data errors are prevented. This is a list of the commands that are supported. I won't enumerate them. But worth noting is that the very first command is number 2. 0 and 1 come before it, and they do something weird. There are also a couple of extra commands that might fit after get chip ID, because the command space isn't filled. I think that it is filled internally because in a later revision of this protocol, they renamed one of the functions. This pointer doesn't work very well. There's a step replace instruction. Here's a clearer list for you. Step replace was actually replaced with a new instruction that does DMA transfers to the chip for very fast programming. And they had to remove this because they filled up everything else. I haven't yet checked those others, but it's worth looking into. So in this command list, and I'll jump back to it for just a second, you'll notice that there's nothing that directly reads or writes memory. And there's nothing that writes the program counter. So if I go back here, you see you can read and write the configuration register, you can erase the entire chip, you can get the program counter, but you can't write any of these things. The reason you can't is because you can do the same thing by debugging machine language code. So you actually use debug instruction to run individual fragments if you want to read or write RAM. And if you want to read or write flash, you just write a bunch of executable code into RAM, and then you jump into it, and you let it do its thing. This is the function that actually reads a value out of internal RAM. The 8051 has 3 or 4 memories, depending upon how you think of it. There's internal RAM, of which it has 256 bytes, external RAM, which can be up to 64 kilobytes, and code memory, which can be 64 kilobytes or more if they have banking. So the first thing that I do is I clear the accumulator. And I do that by executing E4. And 0xE4 is clear the accumulator as an 8051 byte instruction. If you put that into a machine language program, it will clear the accumulator. And it takes no parameters after it. The next thing that I do is I move the value in memory at the address I'm interested in reading into the accumulator. And then I wait a couple of clock ticks after. The first parameter of the debug function, ccdebug, that describes how many bytes I want to send, but it also tells how many clock edges I want to hit. So even though this 0 at the end is not part of the instruction, it's necessary for me to get the accumulator value back. And that's how I read a value out of RAM. You can do the same thing to write flash memory. You do it by writing all of the page that you want in flash memory into RAM, and then copying it in bulk using a program that you've loaded into RAM after it. And they provide an example program for you in the documentation. So this is what the program looks like. You actually just have comments and bytes. And then on the far edge in comments, you've got the meanings of this. So if you flip between the two on a wide display, you can actually see both the machine language and the disassembly. And if you take the time to do it, you could even write this fragment in C, having a compile and then link into the debugger. There's a security feature of this protocol, though. And it's the security features that make these things interesting, because you have to have something to break. You have to have a challenge. Here, the debug lock is read as the chip turns on, and it's required for halting and resuming the chip and for running your own instructions. So the idea is that you can't read or write memory unless the chip has not been locked. And you can only unlock the chip by erasing the entire chip. And this is part of the status register. If you set the debug lock, you're writing a bit of EEPROM that gets erased during the debug erase, but it doesn't change that status register bit. So you can actually lock the chip, then program it, then power it down, and it's locked and ready for distribution. At the same time, if the bit is read wrong at startup, it stays wrong. So if you load it up with a bad power supply and it fetches the wrong bit out of that EEPROM, you stay in. You can read and write memory till kingdom come, and it's only at the end, when you power it down, that you're locked out. There's another mistake, and this one I published in the